So there are a few questions in the chat, but Patrick can address them and we can address them later. I think Patrick, there's a concern from Andy about how you make sure you're not swiping in other non-needed, I'm going to call source code, but we can address this later quickly without needing to go one by one. Okay, so what I'm going to do right now is I'm going to first share my screen. Then I need to pull you guys here so I can see you. Perfect. Can everybody see my screen and it's showing Cohort Diagnostic? Perfect. So we shared this link with you. It is in the result.odyssey.org, so it's public for everybody. What we did is we ran those algorithms in addition to others on the J&J available data sources. And so here in the databases, you can see about 7 or so of observational or data sources that we have in J&J. Some are EHRs and mostly are claims, some mostly from the US and some other data sources. For those who have never seen Cohort Diagnostics Shiny before, I'm just going to orient you into the app very quickly. You see here on the left side are the different diagnostics or tabs that you can explore. And then once you click on one, you're going to see a report or data that shows up on this side. You can select the cohorts you're going to look at in case you have multiple cohorts that you ran, and you can select on the data source you want to see the results for. You can, depending on what you're looking at, you can select multiple data sources at the same time, and sometimes you can also select multiple cohorts at the same time. And sometimes you can select multiple cohorts and multiple data sources, depends on the diagnostics. So there are multiple diagnostics here, and I'm not going to go over all of them. I'm going to show you what we can look at to just roughly understand how did these algorithms that Patrick built end up showing or manifesting in the data source, capturing which patients, how many patients, and stuff like that. So the first simplest question to answer is how many people I'm capturing across these different data sources, and how do these numbers vary by the algorithm? Intuitively, we can think of the CCW 30 that require 2 diagnoses being the most strict in principle, because it has a narrower list of concepts that says that you have to have Alzheimer's disease and didn't include codes that are in the dementia unspecified realm, focus on only Alzheimer's disease diagnosis, as Patrick shows us, and it requires 2 diagnoses or 1 diagnosis in an inpatient setting. So you can think of it as the most strict, at least in principle. We don't know how that manifests. The 27 CCW is the first one he built, which is 1 diagnosis of Alzheimer's disease on any claim. And then you have the last one we built, which is Harris, which has a complex logic, but in general, it has a broader list of codes because it includes those senile dementia, degenerative disease of the brain, in addition to Alzheimer. And then you can enter if you have 2 treatments. So you have more, in theory, possible ways to enter. I know Patrick said that just to recap in case people lost what were the logic of each of those 3. So now you can see how that manifests in terms of counts. And that's the tab you get if you click on counts here. I selected the data sources, which is all of them I have access to, and I selected those 3 in specific because that's what we're focused on. So if I pick the very first data source right here, which is our data source come from Germany, which is GP specific, you can see that I am using the 30 CCW. That's the most strict in principle. I'm capturing about 44,000 patients. You can see that now number goes to up to 106 patients once I go to 27 CCW. That's the difference between a 2 code and a 1 code in Germany. And now I see that I jump up to 146,000 if I used Harris algorithm. So that is a big jump in terms of counts. That's not always the case. So I'm going to go to Japan, which is the second data source here. You can see the differences are slightly less in terms of the magnitude. So I have about 9,400 if I use the 1 code logic. I jump to 10,000 if I'm using if I'm using the 2 codes or inpatient. I jump to 10,000 if I went to 1 code only, and I jump to 16,000 if I go to Harris algorithm. So you can see that the jumps here are slightly less, but still you have a significant difference in terms of the magnitude of how many patients you're picking. I can look at one of the US data sources claims. So for example, if I went to DOD, Optum DOD, it claims US data source that covers multiple ages. You can see that I have about 700,000 jumps to 800,000, jump to about more than 1 million. So you can see here the jump. So I did the math across all the data sources, and I can roughly say that going from 2 codes into 1 code adds about somewhere between 11% extra patients to 50% extra patients, depending on the data source. And if I go to Harris, from going from 1 code of specific Alzheimer to treatment and a broader set of concepts for Alzheimer that includes dementia or unspecific dementia, I'm going to jump anywhere between 40% to 70% extra people. So you're clearly going to pick up different magnitude of people depending on which algorithm you're going to use in your study. We can look at this. Somebody might say, well, the count doesn't matter. What really matters is the incidence of the case. It's the incidence of the events, how much that affects the risk of getting Alzheimer or the incidence of the event in these data sources. So to do that, you can go to the incidence rate tab. And what I'm going to do right here is that for simplicity here, because we're going to look at multiple numbers, I'm going to pick one data source. I'm going to pick DOD. And I am going to pick the 3 different definitions. And now here you can see those numbers stratified by age and sex and calendar time. We know that this is important in any incidence rate or epidemiological trends, because obviously age and gender are a big fact, and you want to kind of control for that when you look at the difference among data sources, for example. And then you can also simplify this because it's going to give you very old ages. So for simplicity, I'm gonna, and that caused some statistical instability because we have low counts on those denominators on those old ages. So I'm gonna pick that. I'm gonna also remove people with no gender. That's something that we have only in German databases, but I'm gonna simplify this. I'm gonna also remove the last year because usually the last year have some instability associated with it because the data is not yet complete. And then I'm gonna generate the report. I'm gonna use the same Y scale so we are able to look at the different differences. So I'm gonna unify that. I'm gonna also go down a little bit on the scale just to make these pictures look slightly clearer. Report again. Okay. So here you see one data source only. I'm looking at the 3 different algorithms, and I'm looking at stratified by age and gender. I'm gonna make this bigger a little bit. Okay, this went to 50. Yeah. So one thing I can do quickly, just for visual, is I can see that because Alzheimer is a disease of older people. Here the Cohort Diagnostics give me all ages, but it makes sense for Alzheimer. If I'm just gonna look at the incidence, I can remove people with younger ages just because they're technically not at risk. And that's gonna make this visual slightly nicer. Okay, perfect. So now we're looking at 60 people 60 and above, and we're looking at the difference of incidence presented here on the y-axis using incidence rate per 100,000 person year. And here are the different definitions, and here are the incidence over time. There are multiple things that you can look at, but for now, I'm really just interested of how these different algorithms led to what incidence rate and if it varies. So I can look at people 80 at 89 because they're just the population of interest for now. And I can pick 1 year. So let's pick 2017. And let's pick men. First of all, I can see that men are at more risk of Alzheimer's than women, which is great because that is actually a known fact. And I can see it in the data. So it gives me some sanity checks. So 2017, I see among men, I see for that year in particular, the incidence rate is about 39.65 using the CCW 30. So let's look at CCW 27. Now the incidence went up to 45.38. So it went up a little from 38 to 45. Now if I look at Harris for the same year, for the same subpopulation, now it jumped up to 91. So that difference in magnitude in DOD of how many people we captured almost went, what is it, threefold? Less than that, maybe two. So we had 21, yeah, at least twofold, from 35 to 91. So we went we doubled the incidence rate of the event, and that's one data source, depending on which algorithm we use. And you can see that that's definitely affect your study results, even if you're looking causal inferences, because you have a different incidence of the baseline incidence of the event itself, or you're trying to report on the background incidence rate of the event. So using that, which algorithm can really affect the study results? Okay, I'm now gonna jump into something that maybe one might ask, when we looked at the way that people could enter these different cohorts, which one of this difference in logic or concept really made that, which one is more responsible for that difference in incidence or that difference in count? So one can look at something called index event breakdown. This is a summary that gives you, among all these different entry criteria that you put in, measured at the code level, concept level, what is the distribution of those codes? So that it can give you an idea of that entry criteria, which entry criteria accounted for most of the cohort, people in the cohort. Or you can look at just the distribution of that. So I'm again gonna, in this case, I can actually pick multiple data sources, but let's stick to one. And in that case, I can only pick one cohort at a time. So I'm gonna go to Harris because it's the one that has really multiple, a whole long list of codes, and you can come in if you are on treatment as well. So here is Harris. So again, this is the distribution, the proportion of people who had any of the possible codes that were part of the entry criteria. I can look at it using standard. I can look at it also using source. So to Andy's point that he was a little bit worried about what are these other source codes that might have mapped to the standards that I included, and what if I included something I don't want? So that distribution helps you answer that question, because it shows you from all these different possible ways that Patrick ended up putting in that algorithm, what are the things that are showing up. So that can quickly tell you if there was a code that is absolutely should not be in Harris or any of the other algorithms that swept in and represent a meaningful proportion of the population. Does that make sense?
Can you click on non-standard, Alza?
Yeah, and you can see that in non-standard in specific if you want to see things in the non-standard. So I'm picking here Harris. I'm looking at the DOD data source, and I can see and I can sort this. In different version of Cohort Diagnostics, these numbers were rounded at night. In this one, it's a little bit, we have a very high precision, but you can do the math. So I see here 26%, 4% of the people entered because they have this unspecified dementia, unspecified severity, the F03.9 ICD-10 code, which is absolutely was enlisted in their paper. You have 7% coming from Alzheimer's disease. You have 6% coming with degenerative disease of nervous system. Again, a very broad idea, ICD-10 of G31.9, but it was absolutely listed in that paper. And you can go on, but you can basically compare this list with the list listed in the paper to make sure that everything included are actually what the paper listed, and you're not sweeping in source codes that shouldn't be there or any codes that shouldn't be there. What I want you also to see is that it makes sense that the doubling in incidence rate once you go to using a Harris algorithm, because you can see that Alzheimer's disease, which is the main code 331, in the ICD-9, which is the basic Alzheimer disease, is only 7% of the population once you allow these other codes to be in, once you allow the treatment to go in. So it's no surprise that your incidence doubled and tripled in some cases, because the proportion of people with Alzheimer end up presenting a much lower proportion of the overall population once you allow all these different criteria for entering for Alzheimer. One might ask, though, does that make sense? Because there is this clinical knowledge that somebody said that Alzheimer's disease represents 60% of people with dementia. So that from here tells you, wow, this is what I'm seeing in observational data is not really consistent with what people say about Alzheimer being the biggest portion of people with dementia. But that might be because people use the codes of unspecified dementia for people who truly have Alzheimer. We don't know that, but it tells you how the distribution of these codes are in a certain way that may be different than what you expect, given the clinical definition of things. Okay, I only have 6 minutes, and I will show you something else that you can look. One might ask, okay, I have a very different distribution. I have a very different magnitude of the event, incidence of the event. Am I roughly picking the same kind of people? And by the same kind of people, I'm going to just answer the question, the demographic of these people, because there's this idea that dementia is more present among maybe younger population, while Alzheimer is older. So maybe let's look at the age distribution of the 3 different population or cohorts. I'm going to go to compare characterization, and I'm going to pick, in this case, it's 1-to-1. So I'm going to pick Harris, and I'm going to stick to DOD just because it's the one that we looked at, and I'm going to compare it to, let's do CCW 27. And then I'm only going to look at demographics for now. So I am going to just do what we call time invariant. So those are the variables.
You have to change the database on the comparator.
Oh, sorry. I think you got them. Yeah, it allows you to even compare cohorts across data sources. So I'm going to use only time invariant because this is demographics, and I'm going to pick only demographics, and I'm going to generate the report. My intent just to look at the age and gender. Oops, I'm going to look at table. You can look at the plot or you can look at the table. So I'm going to filter here just to age, because it's going to also give me the years, because that's another demographics page. Nope. Okay, so here it's giving me the age distribution, and it's giving across the target and the comparator. Our target, we picked our target being Harris, and our comparator being 27 CCW. So that's the one code. It's giving me, we have 10 different age groups that exist in the standard featured for age in OMAP. And you will see that roughly the distribution is the same. If you're using standard deviation of more than 1, you can see that it's just in the target that is Harris. You have slightly more proportion of people in this younger age group. So that is 1%. If you look at the those older age groups, you see that Harris is picking 27% being in the 85 to 89, while CCW is doing 31. Here you have 3% of those older versus 5%. So there's some variation, but it's not striking. And if you use standardized mean difference to quantify that, roughly you're under the 0.1 other than that younger age group. But you have more people in the younger age group using Harris, which could be maybe telling you that you maybe are picking people with dementia that are not really Alzheimer, because those are the people, the main difference between any dementia and Alzheimer is people with Alzheimer are the older population. So maybe you have some some of that. But there is now a big change. If I look at gender, I forgot, is it? Yeah. You can see the distribution of gender is basically the same. 61 being female to 38 in Harris, 64 to 35 in CCW. So even though you change the magnitude of the people you're picking, change the incidence rate, had different distribution of how people enter the cohort, your your gender composition is still the same, which is good. Your age distribution is slightly different. Okay, you can do this for every single code in the data source. You can look at the distribution of every single event using this tool, but that's a lot. And I just wanted to show you how you can do this for demographics, for example. You can see it for every treatment, every procedure, types of visits, and so forth. And now to try to understand, did the algorithm led you to different characteristics in the people you're capturing? We all already understood that we're definitely capturing different magnitude of people. And we're at time, and I should stop here. Okay. We can open it up if somebody wants have a stressing question about this. How do you guys feel? I know Cohort Diagnostics has a lot. Patrick went through Atlas a lot. Quick.
It's a very high level. There was a bit of a drop in the Harris in 2011, so not near any ICD-9. Could that be related to drug availability data in the Optum resource, as such the donepezil, rivastigmine, memantidine prescription data decreased, and that's what sort of decreased that trend out?
Yeah, absolutely. So one thing we look at is the stability of the algorithm over time. And Kevin picked on something important, because generally, if you're using it for a study that spans over multiple years, you want to make sure that your algorithm is stable. And often we see those changes, and then you go and try to explain why these changes happen. We usually have that change between 2015 and 2016 because of the ICD-10 or 9 transition, 9-10 transition. But yes, you'll see others, and here Kevin picked on the 11, and that probably related to the treatments. Yeah.
Hey, Azza, real quick, can you speak to the importance of, I get the comparing cohorts, different definitions, but maybe when you have nested cohorts, of the importance of looking at patients who enter one cohort but don't enter the more specific cohort as a form of diagnostics?
Yeah. So we usually use the cohort diagnostic to try to evaluate cohorts. Here, in this case, we were just using to see the differences in different algorithms in the literature. But if you're using the tool to evaluate two different algorithms and try to understand the difference in the two in terms of, are you picking more wrong, false positive, or are you missing some true cases? What you really need to compare is not the two algorithms, because often there is an overlap. What you really want to compare is the people that you're adding in one algorithm on top of another algorithm, for example, just like the CCW30 and CCW27. So you might want to throw in your cohort diagnostic those people who actually have one diagnosis and doesn't have two. So those are the people that you are adding if you use CCW27 and not using CCW30. And those are the one you want to compare with the CCW30. The reason why you want to look at the differences between two sets of people who meet one criteria and not the other, to see if those are true positive or true or false positive. Otherwise, if you compare all CCW30 with 27, you have about 50 to 70% of the population exists in the two cohorts, and you will be comparing the same people, so you will not see any differences by design. If you really want to compare two algorithms, specifically if there is a huge overlap, just in the case of one being a subset of the other, you really want to look at that marginal population, the people you're adding in one versus the other, and then compare their characteristics, because that's where you're looking at what are the true differences, removing that overlap.
Thanks.
In this case, we didn't do that because that's not what we were looking at per se. We were just looking at if there was a great overlap, that's great because we want these people to be the same. Sorry, somebody started talking and I stopped them.
Okay. I'm going to stop the recording as
Okay, so thank you everyone for joining.